Our next speaker is Professor of Mechanical Engineering in Mohawk. Robert has been in the forefront of additive manufacturing, or better known to most of us as 3D manufacturing, which is really revolutionizing the way we make things and produce things and potentially in future sell things. Maybe instead of selling products, you actually sell the CAD drawing to a product and people can actually produce them in their home or in their businesses. Mohawk College has received a lot of funding to establish state-of-the-art additive manufacturing institute, and Robert is going to tell us a little bit about the design and the future of additive manufacturing. Robert, thank you.
All right, good morning. So, Professor Robert Gerritsen, School of Mechanical Engineering at Mohawk College. I'm also the coordinator for Mohawk's brand shiny new Additive Manufacturing Resource Center. So today I'm going to talk a little bit about the Resource Center, so who we are and what we do, and then I'm going to talk a little bit about the world of additive manufacturing, in this case particularly from the vantage point of design. Now, I'm not talking about the rules of design, that's a very complex area altogether, but more how design is going to establish itself, or more specifically how design will evolve to be one of the key drivers in our area or in that technology. So tell me, who here hasn't heard of 3D printing? Yeah. Pretty tough topic to avoid with all the media press, all the media exposure that we've got today. Lots of disinformation out there. Maybe I'm going to try and clear a little bit of that up and paint a picture of where this industry is going. Again, we're looking at one of the potential revolutionary developments with respect to manufacturing. So take a look at our resource center. We are located in Hamilton. We're here at the Fennel campus. A little bit about Mohawk, for those of you who are not familiar with who we are. 6th largest college in Canada, about 13,000 or so students at any one time. We are also the largest institution dealing with skilled trades and apprentices. Turn out about 4,500 apprentices and skilled trades individuals per year. We have 4 campuses within the college, and we've also got about 130 or so full-time programs. Within the college, we look at our ratings with respect to how well we're regarded by industry in general. We've got about a 93% or so industry rating. So our students are held in very high regard by industry out there. We also then turn back and look at our students. So what kind of reputation do we have with the folks who are attending our institution? And we have, over the last 5 years, been awarded the #1 college within the greater Toronto and Hamilton area. So again, a very very well-founded organization that we've got here. Absolutely state-of-the-art facility. We arguably have one of the finest labs in the country for exploring 3D printing and additive manufacturing. Sorry, go the right direction. Second institution in Canada with what we call a direct metal laser sintering technology. So we've got the tools to take that idea of what we would typically hear in the press about producing a part out of plastic, and we can do that now out of metal. Our colleagues over at Nova Scotia Community College beat us by just a couple of weeks. So we're the second folks in Canada with that, the only ones in the region academically with access to that technology. We're also the second institution in our region with access to a large-scale industrial strength, what we call SLS, or selective laser sintering technology. This is now a robust, state-of-the-art industrial strength plastic technology to produce the typical parts now, not for samples, not for props, not for rapid prototypes. Our concentration is on the additive manufacturing side, where we're looking at producing end-use products for specific applications. We're engaged primarily in applied research and design, right? So we do work for industries, typically the local firms, although we've started to have some national reach as well. So we've done some work with some folks, for example, out in BC. That applied research side is looking at the direct applications of our technologies, and then we're also, as a parallel path, engaged in the education. So we're looking at turning out, again, as a evolving, emerging technology, the future crop of engineers and designers that are going to participate in that field and help foster the growth and adoption of that technology. So we're involved really in both of those areas altogether. I want to start taking a little bit of look at the differences between additive, or why that word additive manufacturing, and how that differs from what we typically have as our conventional processes today. Now, We'll see if my little animations behave. They've been a little problematic over the last little bit. And if we look at the comparison between what we'll call our subtractive or our conventional technologies, these are typically the way that we will produce parts today. Literally the machining, the casting, the filing, the grinding, right? The typical operation of parts that we put or that we assume with conventional manufacturing. Literally, we're taking a billet of material and we're filing and carving or removing material to produce our given part. If we compare that to additive, additive speaks to the technology in one of two ways. We're looking at taking a raw material and actually adding it to itself to generate our part, or have that part grow by the addition of material as opposed to removing it from something that already existed. And we're also looking at that additively in terms of how those objects are constructed, typically layer by layer or slice by slice at a time. In this area, we've got three primary technology columns or technology verticals. On one hand, we've got a realm of typical desktop do-it-yourself hobby-type systems characterized by the MakerBot systems that are out there, typically referred to as our 3D printing technology. We've got a middle-range professional-grade systems that talk about the creation of rapid prototypes. They also come with that name, 3D printing. And then finally, we have our state-of-the-art industrial strength technologies that pick up that name with respect to additive manufacturing, so the production of end-use products for given applications. Let's take a look at a couple of things. So what isn't, right? What does additive manufacturing not represent? Well, it ain't Star Trek. Parts just don't materialize out of nowhere. There is no just push print and have part, or there is no tea, Earl Grey, hot kind of idea. That's just not the way additive manufacturing creates the objects that we're looking at producing, right? Nor is it going to be a silver bullet. It's not going to be a technology that's going to bring all the jobs back on shore, right? It's just not that kind of a robust technology, right? It's not the right tool for every job, right? And that's one of the misnomers, and that's one of the impressions that the press is putting out there to society at general, that additive is an end-all and be-all as far as manufacturing, right? If we've got a typically machined part, something that conventionally be produced with our given subtractive technologies, that's still going to be your fastest, cheapest way to produce that particular item, right? Or if we're looking at mass production, we need the million or couple of million parts per year, then injection molding or die casting or one of the other, right, mass production technologies is still going to be the right tool for that particular job, right? Additive is just not going to be an end-all and be-all, right? What additive manufacturing really is, or what represents, is a technology that's going to be deployable, or a technology that can be applied to very specific jobs. And those jobs are generally going to be the ones that deal with a high degree of complexity. We've got really complex forms or really intricate parts and profiles and so on. This is where the heart of additive manufacturing has got its contribution. This is where it really can make a statement in terms of dealing with complex or new forms of parts. Right? One of the typical ways that I will describe it, right, is you can't drill a curved hole. But with additive, my button's right here, with additive, we can very easily print one. And that really speaks to a whole new mindset in terms of designing parts, a whole new way of finding solutions to problems that we've got out there, right? Ways that we can now deal with internal complexity, right? Very complex forms and so on. Essentially, we're developing a new and novel combinations of form and functions in the parts that we're looking at. That's going to be a very important statement in the next little bit, because we'll show you that we've been at that point before. We can learn a little bit from history where we've had a technology that's allowed us to explore new forms and functions of parts, right? Now, it also means different things to different individuals, right? For the engineer, for example, if we look at a conventionally designed component, now I've picked a couple of the iconic parts out there that speak to our additive manufacturing industry. This happens to be a hinge for the next generation Airbus. In the conventional manufacturing and design of that part, we would have a part subtractively manufactured component. Again, we remove material from a billet to essentially produce that item. Utilizing some very sophisticated design tools, we can take a look at that part and say, yeah, you know what? Not all the mass, not all the stuff in that part actually carries a load, right? I can get rid of some of those items. And those become incredibly important for applications such as aerospace, right? If I've got to hoist a part up into orbit, it's thousands of dollars for every kilo that goes up into space. So I can shave a couple of grams off of that part. That's going to be worth huge for this application. Or for the aviation, in this case, for every gram that we've got to haul around, right, that comes with a fuel cost or a fuel penalty. So if we look at that engineering, we now have the tools in the guise of additive manufacturing the ability to deal with complexity, to produce parts now that give us an inherent advantage in that. Lightweight, high-strength structures, for example. And we can take that concept a little further when we get right into the guts, into the internal concepts of the part. So we look at lattices and open weave structures and so on. That concept of, again, can't drill a curved hole, but can easily print one, speaks to the ability now of optimizing parts, in this case with respect to strength and weight ratios. But it also means different things to, thankfully, the artists and the creatives out there, right? Gives them now a new tool to express designs, to express inner visions, to convey emotions in the parts that they're generating. So now it gives us now another tool in that toolbox to generate those objects or those forms. And for the designers out there looking at our more consumer products, we now have tools that can start to deliver on the promise of more organic, more nature-derived items altogether. So we're starting to see that become established as a tool to take advantage of what additive has to offer with respect to its technologies. We're going to call this an area of biomimicry, right? So the idea of mimicking parts that look like they were generated or formed by nature, right? Combine that technology with a couple of other interesting business aspects. For example, sustainability, right? In this case, when we look at additive manufacturing being a technology that builds the parts out of a raw material, we don't have that grinding and filing and cutting. We're not producing chips on the floor. Essentially, the material that's in your part is the material that you consume. Mine is just a little bit of stuff that we call support. It kind of holds the parts up and holds them together. So we have a very interesting sustainability play with respect to additive manufacturing. A very drastic reduction in the raw materials, a very drastic reduction in the amount of energy needed to produce that given quantity of material, and henceforth a reduction in our carbon footprint or our greenhouse gas reductions. So we have an interesting sustainability play coming into or being fostered by what additive has to offer as a technology. We also have some new business perspectives with respect to how we produce parts, in this case in the area of mass customization. One area that we take a look at, very early adopter for additive manufacturing technology processes, had been in the production of knee and hip replacements. Just about every, or the vast majority of those items today, are produced by an additively manufactured technique. If we're now looking at further exploring that area with respect to mass customization, today we've got knee and hip replacement implants in maybe 3 or 4 individual sizes. With the mass customization idea, we can start combining some other technologies, being the direct importation of CT or MRI data, where we can now produce additively a component tailored to a specific patient application. So we're not picking from a catalog of standard sizes. We now have a device, in this case a knee or hip implant, that may be adapted directly to the patient requirements altogether. Right? And then we can also see this reflected back to some more consumer-aided products where we will still see a degree of uniformity. Again, the iconic iPod case, but customized to the tailored to the appetites of the individual. So the ability to produce these still as a mass product, right, tailored to the needs and desires of the individual client out there. Another area we can look at is this reduction of time to market. Since additive is essentially a toolless process, we can explore different iterations, different forms and different shapes, and do I like the size of an object, without having all the investment in the tool, both in the cost and in the time. Gives us the ability to produce more items in that preliminary style or that preliminary era altogether. We'll start with what we look at the typical as rapid prototypes, the 1s or 2s that satisfy the idea, and then with the additive manufacturing, that ability to produce and use products, we'll move into items that satisfy the requirements for proof of concept or clinical trials or somewhere in that area. And that's one of the specialities that we have within the Resource Center, is we look at the production of quantities that satisfy the needs for, is it enough items for beta testing? Do we get enough out there to really get a good feedback in terms of our product or our design actually good, or do we need to satisfy clinical trial requirements for that particular item? One example of that is looking at changing the world of orthopedics and prosthetic production. So we're in the very early phases with the folks at Hamilton Health Sciences to look at revolutionizing the way that, in this case, orthopedics are produced. Typical process today is we'll take a cast of the patient's foot in this case, produce a plaster model from that, thermal form, or heat up plastic and bend it over that form, and then file and carve and grind and fit and so on until we end up with an orthopedic device that satisfies the patient's needs. Typically, we're looking at a 10 to 12 week process for that, maybe longer in some cases. by utilizing what additive manufacturing has to offer, that very quick production, no tools required, and combine that with some interesting areas in terms of scanning or the ability to take MRI and CT data, we can now look at producing a very specific orthopedic for a patient application, and we want to try and get that down to 48 hours or so, and in some cases we've mimicked this down to a 24-hour cycle altogether. So a pretty significant decrease in the patient wait time, and we can see that reflected also in the generation or the launch of new products as a reduction in time to market. So we're seeing this as a disruptive technology. It's changing the way we're looking at our typical business processes, and it's also changing the way that we're looking at the design of our products. Again, new and novel combinations of form and function, right? What we're really looking at is creating a new and emerging design aesthetic, right? The value in combination with the beauty and with the form of the products that we're looking at. And interesting enough, we've seen this before, right? Industry-wise and society-wise, we've been at that same juncture in the past. If we think back to close of World War II, we had the emergence of plastic materials at that particular point. Had a material that, again, satisfied some very specific military applications at the time, but now was looking for new consumer applications. What the industry had done at that point was turn to the designers of the day, in this case, one of the iconic products that we see from Earl Tupper, right, in Tupperware, and turn to those folks to explore what plastics had to offer in terms of new and novel combinations of form and function. The ability of plastics to produce items that they had not been able to produce prior to that on a new manufacturing platform, that being mass customization. Or we look at another iconic image from Robin Day, right, the polyprop chair, something that we see every day in and day out, speaks to a certain aesthetic with respect to that particular product. Uniformity of design, right, the ability to produce forms that we had not been able to generate before, and then the mass production aspects altogether. So what we've seen is disruption in design drove the growth of plastics to what we see as one of the dominant manufacturing technologies today. And we're at the verge right now where disruption, or a different way of thinking about our business processes, as well as design, that new and novel combination of form and function, will be one of the key drivers for additive manufacturing as we go forward. All right. Some of the challenges and opportunities that we're faced with in this industry right at the moment, one is on the material side. Right? Additive manufacturing still has a limited library of materials. We don't have thousands and thousands of steel alloys or plastic materials out there. It's got a limited library. On some of the metal ones, it's probably down to about a dozen or so materials altogether. But on one hand, if we have a disadvantage in the library of materials that are available, we do have an advantage in additive manufacturing to deal with some very complex materials. For example, it deals well with titanium, a notoriously tough material to deal with on the subtractive or conventional side, right? Offers some ease of use with respect to additive, or some of the biocompatible materials, calcium phosphates and so on, are readily produced with additive manufacturing techniques or formed into end-use products. We also have a limitation in our software. The tools that we're using today to generate that new and novel combinations of form and function, right, they're still geared towards the manufacturing of conventional processes by conventional means. So we're looking at an evolution in terms of now products that deal with that much more free-form, organic, that biomimicry statement altogether, in addition to the additional software demands that we've got with transfer languages, right, so good tools to change files back and forth, as well as the amount, the size, and the storage of information that we've got with a toolless, with an e-manufacturing solution, the requirements that are going to come with that. Speed is also a limitation, right? It's not a robust technology today to take on injection molding or high-speed CNC applications. So we're still looking at the development of strategies that optimize how we actually produce parts. Limited build envelopes and strategies in terms of how we can combine multiple components in a single operation, a single run of our machine, to give us the parts that we're looking at generating. We're also looking at reliability. This is not reliability in the process. Additive is inherently a very reliable, very repeatable process. That's one of its core strengths altogether. But we're talking about repeatability here is in the technology's ability to meet customer commitments. It's still not at the point, and there's still some very early stage work that needs to be done with respect to counting on the technologies, counting on our design, counting on the way that we manage our particular tools and assets to produce a given part for the end customer. One of the areas that we see here is residual stress with our parts. When we produce that part, especially with the laser technologies, they tend to bend and twist and they kind of pretzel in the machine, and we still are struggling today with tools and techniques that allow us to manage those requirements so that we can reliably and repeatably meet on our customer commitments. Education is another area. Again, it's why Mohawk is leading the charge as being one of the institutions out there that's turning out that future crop of engineers and designers that understand the pros and the cons and the idiosyncrasies of additive manufacturing. Again, it's a different mindset, right? Take the gloves off with respect to creativity. Take the gloves off with respect to that combination of form and function that we can look at generating with additive that we had not been able to produce before. Again, think that can't drill a curved hole, but can easily print one mindset in terms of the kind of areas and the kind of solutions we can explore with additive. When we look at the education requirements, it's not only from the design standpoint, however, but it's the entire process from all the way from the design or the creation of content, out to management of the systems, out to quality control and inspection, out to disposal, out to the processes by which we will distribute those parts at the end of the day. So there are educational requirements that are needed in all of those strategic areas. One of the final areas we're looking at standards, again, a relatively new area in additive manufacturing. It's still a little bit of the Wild West with respect to the standards that are out there. We have a number of organizations that are attempting to establish some of the ground rules or some of the criteria or some of the yardsticks that we're going to use with respect to our ability to deal with the technology. So standards is still an area that is continuously evolving and establishing a little bit more of a presence so that this becomes a reliable technology in the same mindset that we have others. So really, at the end of the day, as the individuals that are invested in pushing this technology forward, making this one of the next manufacturing revolutions that were out there, we will think we have done a good job with this technology when we get additive manufacturing to be in the same mindset or to take its place shoulder to shoulder with our conventional technologies such as CNC or injection molding. That position is still as yet to come. All right, there's still a fair amount of developmental work that needs to happen, but again, we're right in the early days. We're right at that formative stage where the technology is rapidly advancing towards that kind of mindset. Again, the same kind of inflection point or the same kind of juncture where we were, again, post-World War II with the development of plastics. We're in that same position right now with additive, and we can learn from the past with respect to how design was a key driver for plastics, will become a key driver for additive manufacturing as we go forward. Thank you very much. All right, appreciate the opportunity to speak to you this afternoon, and again, have a good afternoon with our reporters competition. Thank you. Thank you.